A hanging balance often symbolizes fairness, and a lot of people have strong opinions on what exactly is fair. Even if we focus on the problem of fairly allocating resources like apples and oranges, researchers don't have a clear way to answer a simple question. What's a fair way to allocate resources? There's even more complexity in network resource allocation, where multiple users and multiple resources are involved. Our work develops a framework for systematically studying the allocation of multiple resources. Compared to the allocation of a single resource, this question hasn't been addressed much in the literature. Our contribution is a mathematical framework built on a few fairness axioms that unifies previous ways of thinking about multi-resource allocation and also proposes new ones. By resources, we mean anything that can be allocated, for instance, data center CPUs, or RAM, or even virtual machines. Or you could think of resources as links in a network and address the problem of allocating bandwidth to network flows, sharing different subsets of these links. More generically, let's say we have to allocate apples and oranges among different clients. These combine to process jobs for a client. For instance, 2 apples and 3 oranges might make apple-orange juice. For a different client, 2 apples and 1 orange can make a fruit salad. So given that resources combine to complete jobs for different clients, we have a fundamental question. How do we allocate the different resources? Let's see what's the fair thing to do. If we give 2 apples and 3 oranges to our first client, he gets a glass of orange juice. Then we give 2 apples and the remaining orange to the second client, and she gets a fruit salad. This seems fair. Both clients get one job. But there's a second consideration here, and that's efficiency. If we give all the apples and 3 oranges to the second client, she gets 3 fruit salads, while the first client gets nothing. So we end up with 3 jobs total, but this allocation isn't very equitable. This fairness-efficiency trade-off happens because different clients have different resource requirements. In our work, we assume multiple resources and clients with heterogeneous resource requirements. And we use mathematics to axiomatically define a family of fairness functions, which encounter different points on the fairness-efficiency trade-off exemplified here. We then prove some desirable properties of these fairness functions, like envy, freeness, and sharing incentive, which are not included in the axiomatic definition. And finally, we went to real users with an online survey. We asked what they thought was fair, and we mapped their answers back to our mathematical framework. The analytical results and detailed discussion of this work are available in our InfoComm 2012 paper titled Multi-Resource Allocation: Fairness-Efficiency Trade-offs in a Unifying Framework. Building on this work, we have created a new website as a repository for information on multi-resource allocation research. It also has an extensive list of papers related to this topic by various authors from computer science, networking, economics, and even politics. We're continually adding to the repository. Please contribute if you know of any interesting work on resource allocation. You can visit our website at scenic.princeton.edu/MRA or email us at fairness.edgelab@gmail.com. We hope you enjoyed this introduction. More importantly, we hope it got you thinking. Our work is really only a small step in the centuries-old question of resource allocation, and plenty of work remains to be done.